In our world, many systems exhibit intricate, large-scale coordination. But fundamental physics tells us that there are only a few different rules that define our reality, and most of them act only on small scales. How does complicated global structure and behavior arise from simple, local rules? We will probably never have a complete answer to this question, but there are many mathematical models which can capture, at least a little bit, this phenomenon of complexity and coordination arising from simple rules. In this video, we will explore one particular mathematical model called percolation, which is what you've been watching so far. Originally, it was proposed by statistical physicists as a model for liquid filtering through a porous medium like soil or coffee grounds, though it's probably hard to see that in this animation. This is a rather simple model, but it leads to some complex behavior which is most easily seen with the aid of computer simulations like this one. Trying to understand this model will lead us to many interesting and difficult questions, most of which will not be answered in this video. In fact, some of the things that we will encounter are still not understood, even by mathematicians or physicists. But by the end of the video, we will at least understand why there's a sudden change in the behavior of the model, which you might have already noticed. Along the way, we will encounter one of the most important ideas in probability theory, that of cleverly coupling together multiple random processes into a single process. But before we do that, we need to actually describe the simple rules which define this model. Imagine an infinite square grid thought of as a graph like this. Now, each edge in the graph will randomly decide whether or not to be deleted. If the edge is not deleted, it will stay in the graph, and we will say that the edge is open. If the edge is deleted, we'll call it closed. For now, let's say that each edge has a 50-50 chance to be open or closed. In other words, the probability that an edge is open is 1/2. And it's very important that all of these decisions are being made independently. So what happens in one part of the network doesn't have any influence over what happens somewhere else. In other words, this is a local rule for deciding whether an edge is deleted or not. Once every edge has made its decision, we get a new graph, which is a subgraph of the infinite square grid. Since every edge's decision was random, the entire graph structure itself is now random. The whole random process we just described is called the Bernoulli percolation of the grid, because each edge in the grid acts like a Bernoulli random variable, which is a random variable that takes on one of two values, either open or closed in this case. What you're looking at now is just one sample from this random process. Here are a few more samples, but keep in mind that we don't really care about any one particular sample. Rather, we want to think about the random process as a whole. Right now it's a bit tough to see what's going on, so let's introduce a visualization trick. Think of the edges in the network as pipes and the nodes as small chambers. If we pump a colored liquid into one of the chambers, it will fill up an entire connected component of the pipe network. This is where the name percolation comes from. The liquid is percolating through all of the open pipes, like how hot water percolates through the spaces between coffee grounds when you brew coffee. This idea also explains the open and closed terminology, since an open pipe is one where liquid can flow. Of course, we can pump different colored liquids into the different connected components of the pipe network, and now we can more clearly see the structure of the network and its connected components. By the way, when talking about percolation, these connected components are called open clusters, or just clusters for short. It's important to remember that the colors we've added are just for visualization, and they aren't actually part of the mathematics that we'll be studying. And again, this is just one sample of the random process that we want to understand, so let's see a few more samples, this time with color. In this random process, each edge has probability 1/2 to be open. But what if we change that probability so that more or fewer edges remain open? Specifically, let's pick a number p between 0 and 1 and redo the whole process, keeping each edge open with probability p, and closing it or deleting it with probability 1 - p. This number p is now a parameter for our model, and we'll use this collection of symbols to denote the probability that some event happens in the Bernoulli percolation with parameter p. Here are a few samples of this process now, with various values of the parameter p. For lower values of p, we have fewer edges, and therefore we have more distinct clusters and more colors on the screen. On the other hand, for higher values of p, we have more edges, and so we get fewer distinct clusters. For high enough values of p, it seems like there's basically just one big cluster. Okay, it's still a bit hard to tell what's going on. Let's introduce another visualization trick, our first coupling of this video, which will also be helpful for proving things about this model. Start as before with an infinite grid, but this time instead of drawing the edges, we've just put a faint indication of where an edge could be. For each of these potential edges, let's generate a random number between 0 and 1 uniformly and independently. This defines a new random process, and a sample from this process consists of these numbers associated with each potential edge. And, given those numbers, we can obtain a different graph for each value of the parameter p. Specifically, the graph at parameter p has edges at all of the potential edge locations with a number less than p. A nice way to visualize this is to start with the parameter p equals 0, and let it increase, opening an edge whenever the corresponding number is reached. For our visualization, when multiple distinct clusters are merged, the new larger cluster inherits the color from its biggest constituent. Again though, the colors are just there to help us see what's going on, and aren't actually part of this model either. If we fix a particular value of p, and only consider the graph we obtain at that parameter, then this random process is identical to the Bernoulli percolation with parameter p. Indeed, in this process, each potential edge gets a random number between 0 and 1, and the edges open in the graph exactly when the random number is less than p. This happens with probability p. In other words, the probability that any given edge is open is p, exactly what we had before. The benefit of the construction with the random numbers is that the graphs for different values of p are now coupled together in a very nice way. Given any particular sample of the random numbers, we obtain a different network for each possible value of p, but the network corresponding to a smaller value of p is always a subgraph of the network corresponding to a larger value of p. When p increases, we can only add edges, and we can never remove them. For this reason, this coupling is sometimes called the monotone coupling, because it increases with p. But the more common name in the literature is the uniform coupling, because the numbers at the potential edges are chosen from a uniform distribution. Let's zoom out a bit and see a sample of the uniform coupling at our previous resolution. The uniform coupling now allows us to see the evolution of the Bernoulli percolation more clearly as p changes. Since they would be too small, we aren't showing the numbers on the potential edges anymore, but you should still imagine that they are there. Finally, let's zoom out a lot. Now every pixel on the screen represents a different node in the grid. The edges are too tiny to show, but they're still there, determining which nodes are connected to each other, and hence determining the colors of the pixels that you see. As before, p represents the probability that an edge is open, and it is also approximately the proportion of the edges in the network that are open, out of all the potential edges in the grid. As before, when p is small, we see many tiny clusters. And when p is large, there is just one dominating infinite cluster, which takes over very rapidly. In essence, there are two different phases of behavior for this model, like how water can be a solid or a liquid. Water undergoes a phase transition at 0 degrees Celsius. Above that temperature it's a liquid, and below that temperature it's a solid. In most situations, you won't find ice which is hotter than 0 degrees, or liquid water which is colder than that. And similarly, the Bernoulli percolation on the grid seems to undergo a phase transition. Below a certain critical value of p, it consists of many different tiny clusters, and above that critical value there's just one infinite cluster. From another perspective, if edges represent interactions between nodes, then for low p there are few interactions and the behavior is disordered, like liquid water, with a huge mess of many different clusters like individual molecules just slipping past each other. But once there are enough interactions, suddenly most of the nodes in the grid can interact with each other through some path, and there is long-range interaction in the network. This is a highly coordinated and ordered phase, sort of like solid ice. This already inspires many questions. For instance, what is the critical value of p where the phase transition happens? And how can we even make sense of that question? What defines the two phases that we're seeing? Also, will there ever be more than one infinite cluster? How fast does the phase transition happen? How large are the clusters before they merge? It turns out that many of these questions have been answered. Computer simulations like the one you're looking at led researchers in the 70s to conjecture that the critical parameter is 1/2, and this was first proved by Harry Kesten in 1980. Specifically, he proved that in Bernoulli percolation on the infinite square grid, if p is less than 1/2, there will never be an infinite cluster. And if p is greater than 1/2, then there will always be an infinite cluster. Since Kesten's proof, lots of work has been done, and in the 80s it was also proven that the infinite cluster is unique, so there will never be two distinct infinite clusters. These other questions have also been at least partially answered, and progress on related questions continues to this day. In fact, just last month, Hugo Duminil-Copin won a Fields Medal for work involving percolation, although his work was more focused on a related but different model from statistical physics, called the Ising model. The Ising model describes how tiny magnetic elements can form a large magnet, and it is one of the many other statistical physics models that exhibits a phase transition. In most of these models, just like with percolation, many local interactions between small components induce large-scale coordination. Also, the large-scale coordination only appears for particular values of the certain parameter, such as p in percolation or the temperature in the Ising model. So, like percolation, there's a transition between a phase without large-scale coordination and a phase with large-scale coordination. The statistical physics that goes into even defining some of these other processes is often very technical, so one of the roles percolation plays is as a simple toy example whose behavior is analogous to these more complicated models of the real world. All that is definitely not to say that percolation is trivial. For instance, let's take a closer look at the percolation process exactly at the critical point between the two phases, when p is exactly equal to 1/2. It is known that at this critical threshold, there is no infinite cluster. However, just by zooming out, we can see clusters of wildly different sizes, and critical percolation seems to exhibit a type of self-similarity, where at all large enough scales, the shapes of the clusters sort of look the same, in a probabilistic sense. The boundaries of the clusters also seem to be rough and even fractal-like. These are not precise statements, and a lot of advanced mathematics is needed to even write down what we're trying to say here mathematically. But even if we did that, nobody has proved that this self-similarity actually holds for percolation, even though the analogous statement has been proved for some other statistical physics models, such as the Ising model. By the way, all these questions can also be asked for the three-dimensional grid, where the situation is understood even less. There is still the same type of phase transition, but the critical parameter is not 1/3 or 1/4 as you might have guessed. In fact, it is about 0.2488, and nobody knows an exact formula for it, or even if such a formula could possibly exist. Additionally, the question of whether or not there exists an infinite cluster exactly at the critical parameter is still open, although most researchers believe that, like the two-dimensional grid, there will not be an infinite cluster at criticality. Beyond the three-dimensional grid, one can even consider percolation on an arbitrary network, and there are even more open questions in this broader setting. I hope that by now you understand why Harry Kesten said in 1982 that percolation is a source of fascinating problems of the best kind a mathematician can wish for, which are easy to state, but whose solutions are difficult and require new methods. We definitely don't have time to discuss all of the problems that arise in the study of percolation, but we do have time for one more thing. The rest of this video will be spent proving mathematically that there is, in fact, a phase transition in the two-dimensional grid. For the proof, we'll require a bit more familiarity with the basics of probability and of graph theory. Before we proceed with the proof, we'll need to write down exactly what we intend to prove. Recall that this notation refers to the probability of an event occurring in Bernoulli percolation on the two-dimensional grid with parameter p. For instance, this denotes the probability that there is an infinite open cluster in that percolation. Here is what we will prove in the rest of the video. There exists a critical parameter called Pc, such that for p less than Pc, the probability that there exists an infinite cluster is 0. And for p greater than Pc, the probability that there is an infinite cluster is 1. Of course, it is known that Pc equals 1/2 for the two-dimensional grid, but the proof of that equality is much too difficult for this video. We'll just show that the critical parameter exists and is non-trivial, meaning it's not equal to 0 or 1. By the way, the proof we present here is originally due to Rudolf Peierls. Before we continue with the proof, let's make a few simplifications. Fix a special node in the grid, called the origin, or O for short. This denotes the probability that the open cluster containing the origin is infinite. This probability is positive if and only if the probability that there is an infinite cluster somewhere is 1. Here's a rigorous proof of this fact. Pause the video now if you'd like to read it. Intuitively, the reason is that the origin looks like any other vertex, so if the cluster of any given node has a chance to be infinite, then one of the infinitely many nodes in the grid will be in an infinite cluster. And if there's an infinite cluster somewhere, then it could be the cluster of the origin. One more thing. The cluster of the origin is infinite if and only if there's an infinite simple path of open edges starting at the origin. We abbreviate this by saying the origin is connected to infinity, written with a double arrow like this. All this means is that we will actually prove the following statement. There exists a critical parameter, called PC, such that for p less than PC, there is 0 probability that the origin is connected to infinity. And for p greater than PC, there is positive probability for this event to occur. Now think back to our uniform coupling. The coupling can be thought of as a random function which takes in a parameter p and gives back a percolation graph corresponding to that value of p. If we fix any particular value of p and sample the function randomly, then we will obtain exactly the same distribution as if we had sampled from the Bernoulli percolation with parameter p. However, once we've sampled the function, we can vary the parameter p and obtain a family of percolation graphs which satisfies a special property, that increasing p can only add open edges and never take them away. Therefore, for every possible function we could sample, if p1 is less than p2 and the origin is already connected to infinity in f of p1, then it will also be connected to infinity in f of p2. So the probability that the origin is connected to infinity with parameter p1 must be less than or equal to the probability that the origin is connected to infinity with parameter p2. But neither of these individual probabilities depend on this coupling. They are exactly the probabilities that we're trying to analyze. Therefore, the probability that the origin is connected to infinity must be an increasing function of p. We're drawing this probability as a continuous function, and in fact it is, but notice that we have not yet proved that it's continuous. In fact, the continuity of this function is equivalent to the fact that there is no infinite open cluster exactly at the critical parameter. But we will not need the continuity of this function for the rest of the proof. For us, it's enough to know that it's an increasing function of p. Let's just define PC to be the supremum of all parameter values for which this probability is 0. By its definition, and the fact that we have an increasing function of the parameter p, this value of PC satisfies the two conditions of the theorem. However, we must still exclude two possibilities. PC could be 0, or it could be 1. If either of these possibilities were to happen, then there would be just one phase in the percolation model, and there would be no real phase transition. First, let's rule out the possibility that PC equals 0. Notice that if there is an infinite open path starting from the origin, then for any length L, there is an open path of length L starting from the origin, which we will again abbreviate with a double arrow like this. So, for any p, the probability that O is connected to infinity is bounded above by the probability that there is an open path of length L starting from the origin. Let's find an upper bound for this probability. The probability that there is some open path of length L starting from the origin is at most the sum of the probabilities that each specific path is open. And, for any specific simple path of length L in the grid, the probability that this path is all open is p to the L, because all of the L edges are independent of each other, and each edge is open with probability p. Since the summands are all the same, this reduces to computing the number of possible paths of length L in the grid. For the first step of any of these paths, we have 4 options. But because the path must not backtrack, we have at most 3 options for every subsequent step. Therefore, the number of paths of length L in the grid is at most 4 times 3 to the L minus 1. This is just an upper bound, by the way. the bound also counts paths which double over themselves at some point, whereas the paths we want to consider never do that. But this upper bound won't be good enough for us today. Anyway, here's the overall upper bound we obtain for the probability that the origin is connected to infinity. Notice that this holds for any positive integer L, and if the parameter p is less than 1/3, then 3 times p is less than 1, and so as L tends to infinity, this upper bound goes to 0. This shows that for p less than 1/3, the probability that there is an infinite simple path starting at the origin is 0. Therefore, PC is at least 1/3, since it was defined as the supremum of the values of p for which that probability is 0. Now let's rule out the possibility that PC equals 1. For this, we need to introduce the notion of duality. The dual of the grid that we have been working with is the grid with nodes in the centers of all the squares of the original grid, and with edges that cross the edges of the original grid. For consistency with the literature, from here on out, we'll call the original grid the primal grid, to differentiate it from the dual grid. Notice that there is a one-to-one correspondence between the edges of the primal grid and the edges of the dual grid. So, let us define a dual percolation on the dual grid, such that an edge in the dual grid is open exactly when its corresponding primal edge is closed. If we only looked at the dual grid, we would obtain a Bernoulli percolation with parameter 1 minus p. This is another coupling of random processes, although this time we only have 2 different processes, the percolation on the primal grid with parameter p, and the percolation on the dual grid with parameter 1 minus p. Now notice that every finite open cluster in the primal grid is surrounded by a circuit of open edges in the dual grid. So, if the cluster of the origin is finite, then there is some circuit of open edges in the dual grid which surrounds the origin. Let's bound the probability that a simple open circuit of length exactly L in the dual grid encircles the origin in the primal grid. By the same reasoning that we used when discussing simple paths, for any fixed dual circuit of length L around the origin, the probability that this circuit is open in the dual percolation is exactly 1 minus p all to the L. And again, we just have to count the number of circuits of length L in the dual grid which encircle the origin in the primal grid. First of all, any dual circuit must cross at least one primal edge along this path of length L/2 from the origin to the right in the primal grid. If a dual circuit doesn't cross this primal path, then it must have length greater than L, because it must contain the entirety of this primal path in its interior. After it crosses that primal path, there are 3 options for the dual circuit to continue, since again it must not backtrack. And there are at most 3 options at every step from here on out as well. So we obtain the following upper bound on the number of circuits around the origin which have length exactly L. Of course, in this upper bound we are again overcounting by a lot, because we did not even account for the fact that a circuit must finish where it started. But again, this upper bound will be enough for us. Now let's bound the probability that there is some large open dual circuit around the origin of the primal grid. Specifically, let's find the probability that there is a circuit of length at least n, where n is some large integer. This can be bounded by the sum of the bounds we obtained before, and we get the following series. This series converges if 1 minus p is less than 1/3, or in other words, if p is greater than 2/3. If the series converges, then the tail of the sum must go to 0. More precisely, as n goes to infinity, this sum goes to 0. Therefore, if p is greater than 2/3 and n is large enough, then this upper bound is strictly less than 1. What does this mean? It means that for p greater than 2/3 and for large enough n, there is a positive probability that there is no dual circuit around the origin bigger than n. In other words, if we have a big enough box around the origin in the primal grid, there is a positive probability that there is no dual circuit surrounding that box. So, in this scenario, there is an infinite open path in the primal percolation which starts from some vertex in the boundary of this giant box around the origin. There's also a positive probability that all of the edges inside the box are open. Of course, this might be a very tiny probability, but it's still positive. Now, whatever happens inside this big box is independent from what happens outside of it, because all the edges in the primal grid behave independently of one another. Therefore, both of these positive probabilities multiply, and there's a strictly positive probability that something like the following configuration appears. In such a configuration, the origin is connected to infinity. All of this only depends on having p greater than 2/3, and so what we have just proved is that pc is at most 2/3. This finishes the proof that there is a phase transition in the Bernoulli percolation on the grid, and it also gives us a crude estimate of the critical parameter at which this phase transition happens. Specifically, we proved here that the phase transition happens between the parameter values 1/3 and 2/3. If we wanted to prove that the critical parameter is exactly 1/2, we could still use the duality that we've introduced here. The basic idea is that in most cases, when the primal percolation is large, the dual percolation must be small, and vice versa. If the critical parameter was less than 1/2, then there would be a range of parameters for which both the primal and the dual percolations are large, which is impossible. And if the critical parameter was greater than 1/2, then there would be a range of parameters for which both the primal and dual percolations are small. This is also impossible. But the details of this argument get quite tricky, and anyway, this video has gone on long enough. Thanks for your attention, assuming you made it this far. There's so much more to learn and understand here, and we'll put links in the description for anyone wanting to discover more about percolation. Most importantly, remember that mathematics is constantly evolving, and that there are still many more questions to answer, and even more yet to be asked.